Okay, let's go over the last part of kinetics. I know this has been a heavy chapter, so thanks for hanging in there with me. Now the last part, but it's been a fun chapter, reaction mechanism. That's what we're going to go over. Reaction mechanism. What's the reaction mechanism? Basically, reaction mechanism is a path of the reaction. Is going to detail a picture of what bonds are going to be broken and what bonds are going to be formed during the reaction. Basically, how does this reaction happen? This is the final product, but how did we get there? Okay, so that's what a reaction mechanism is. How did we get there? So let me give you an example. Let's say I have 2NO gas plus O2 gas going to 2NO2 gas. Okay, now the thing is that most likely this reaction is not going to happen in one step. That's not very likely that all of these molecules are going to come together at the right orientation with enough energy for this reaction to happen in one step. Okay, not happen. I'm actually going to write it down. It will not happen in one step. That's not very likely. Okay, I'm actually going to tell you the reaction mechanism for this reaction. What's going to happen is NO is going to go and hang out with another NO, and N2O2 is formed. Okay, so NO go hang out with another NO, and N2O2 is going to be formed. Then what's going to happen is that N2O2 is going to go hang out with O2 and it's going to form 2NO2. So this reaction over here is not happening in one step. What's happening is you have two reactions. It's going to happen in two steps. Now, check this out. If you add these up together, what are you going to end up happening? Let's add this up together. You ready? Let's add this up together. Okay, if I add up this together, is there anything I can cancel out? Pay attention to this part. Yeah, I can cancel out N2O2. Do you guys see that? Okay. Now, what is N2O2, by the way? N2O2 is an intermediate. Now, what does an intermediate mean? What it means is it does not show up in a final equation. This is my final equation. This is formed in the process, but it doesn't show up in the final equation. That's an intermediate. Does not show up in the final equation. So far, so good. Okay, so this is my intermediate. I'm going to cross it out. Is there anything else I can cross out? Not really. So let's add these up together. I have NO plus O2. So that would be 2NO plus O2 going to 2NO2. So you want to add this up together. This is what I get. Is this the reaction we wanted? That is the reaction we wanted. So that's great. That is the overall reaction that we wanted. So this reaction is not going to happen in one step. It's going to happen in two steps. When I add up these two steps together, I get the final reaction that I want. So far, so good. And then don't forget, if this N2O2 is an intermediate is something that does not show up in the final equation. It forms in the process and then is used up in the process. Yeah? Okay, hopefully this is making sense. Now, the thing is that there are a lot of elementary steps that leads to the product formation. What do I mean by elementary step? So there are a lot of elementary steps. I'm actually going to write that word down because we're going to talk about that word so much. There are a lot of elementary steps that will lead to product formation. Now, what do I mean by that? You know how like we had NO plus NO goes to N2O2, and then we had N2O2 plus O2 go to 2NO2. Okay. Now, this one right here, this is one elementary step. This one right here, This is one elementary step. I'm actually going to write it down because you got to notice. This is one elementary step. And you'll see later on why I'm emphasizing on this. Because once you have the basics down, it doesn't matter if I get fancy on you, you will be able to do any problem. Okay? So this is one elementary step. This is one elementary step. So a reaction has a bunch of elementary steps that would lead to product formation. Now, some of the elementary steps would be your overall reaction, right? Some of your elementary step would be your overall reaction. So when you sum this up, it was 2NO plus O2 going to 2NO2. What did we do? Again, what we did is a sum. So the sum of the elementary step would equal for the overall reaction. The sum of these elementary steps would end up equal the overall balanced reaction. Yes? Okay. So again, I need you to remember that this is the elementary step. This is the elementary step. When we add up the elementary steps, that's when you get the overall balanced reaction. So far, so good? Okay. So you gotta remember that for me, and you'll see why I'm emphasizing in a little bit. Another term you gotta know is molecularity. What's molecularity? This is what it is. It's basically the number of molecules. Is a number of molecules that must collide in an elementary step. And you already know what is an elementary step. So the number of molecules that must collide in an elementary step. Okay. Now we have different types of molecularity. We have unimolecular. We have bimolecular. And we have intermolecular. You can probably guess what they are. If you're unimolecular, that means you only have one molecule in the elementary step. If you're bi, that means you have two molecules. Ter, that means you have three molecules. Okay? So again, what are we talking about? So these are the elementary steps, bunch of elementary steps. When you sum it up, they add up to the overall reaction. Now, molecularity is how many molecules must collide in an elementary step. Now, let's look over here. How many molecules are colliding in this elementary step? 1, 2, right? 1, 2. Now, the last one, the intermolecular, is actually rare. This is actually rare. Now, why is that? Here's why. Statistically, it's very hard to have effective collision between three molecules. That means three molecules have to collide together at the right orientation, at the right time for the reaction to happen. So statistically, this is very, very rare. 1 and then 2, of course, is easier, but when you have three molecules have to effectively collide with enough energy, that's a little bit harder and harder to find. So statistically, this is hard and is really rare. Okay, we're good so far. Okay, that's nice. Now, let's go to the next part. Again, we're going to keep going with this elementary step. The next thing we're going to talk about is a rate law of elementary steps. Rate law of elementary step. And this is key. Since the elementary step, the process is a single step. So here, for example, this is the elementary step. This is a single step. This is the elementary step. This is a single step. Okay? So since the process is one single step, I'll write this down. Since the process is one single step, and this is where it's going to be interesting, coefficients can be used. Coefficients can be used to determine the rate law. Now, so far, we keep telling you do not use a coefficient for the orders. Do not use a coefficient to the orders. Now I'm telling you, use a coefficient. But again, keep in mind, that's not true for the net reaction. It's just true for the elementary steps, the steps that lead to the net reaction. I'm going to mention this one more time because I need you to really understand that. So, these are my elementary steps that lead to my overall final reaction, right? My overall final reaction, the rate law, I cannot use the coefficient for the order. But for the elementary steps, because it's one single step, elementary step because it's one single step, for each elementary step, because it's one step, you can use the coefficient to figure out the rate law. Now, the reason you cannot use it for the final equation, because final equation is a combination of different elementary steps. So for elementary steps, you can use the coefficients for the rate law. But again, keep in mind, that's not true for the net reaction, just the steps that lead to it. Yeah? Okay. So hopefully I made that clear. Okay, now that you have all the terminology, let's get to it and see what I'm trying to show you. Let's say we have a reaction that happens in 2 steps. Step 1, I'm going to have A plus B go to X plus I. Step 2, A plus I goes to Y. The first thing I need you to tell me is that, do we have an intermediate? Now, before we do that, we're going to add up this reaction, right? We're going to add up this reaction. When we add up this reaction, is there anything I can cancel out? The I cancels out, right? Because they're on the opposite side. You probably remember from Chem 1A, opposite side, the I will cancel out. I don't have anything else that I can cancel out. But I can cancel out the I, they're on the opposite side. So then what I end up getting is I have 2A plus B goes to X plus Y. Okay? That's going to be my net reaction. So far, so good. Now, what is the intermediate in this reaction? Is there an intermediate? The intermediate is I. Again, intermediate is something that does not show up in my net reaction. There is no I in my net reaction. You just cancel that in the process. So I is my intermediate. And this is my my net reaction. So far, so good. Now, I'm going to give you another piece of information for this reaction. I want to say that a step 1 has a large activation energy. Step 2 has a small activation energy. Okay? We are going to talk about this. So one of them has a large activation energy and the other one has a small activation energy. If you have a large activation energy, what that means is that's going to be a slow reaction because you have a huge hump to get over. Now, if you have a small activation energy, that's going to be a faster reaction because you have a tiny bump to get over. Okay? All right, so far so good. So, now what does this mean? So again, large activation energy would be a slow reaction, and a small activation energy would be fast reaction. Now, which step will control the rate of this reaction? What do you think? Which step is going to control the rate of this reaction? If you had to pick one, you have a 50-50 chance, it's not bad odds. Which step do you think it will control the rate of the reaction? What controls the rate of the reaction? Okay, so what controls the rate of the reaction is the slow step. Probably you guessed that right, because you are as good as your weakest link. Remember that. You are as good as your weakest link. If you are on a team, let's say you're on a soccer team, your team is as good as your slowest runner. If you're on any team, your team is as good as your weakest player, right? So the slow step will control the rate of the reaction. Because remember, you're as good as your weakest link. The slow step will control the rate of the reaction. Okay? Now we have a fancy name for it, and we call that, it's good to have fancy name. We call that RDS. Actually, let me write it in a different color so it matters. We call it RDS. What is RDS? What RDS is rate determining step. So RDS is rate determining step. Basically, it takes time to happen, right? Your slow step is what's kind of holding you back. It takes time to happen, but once you get over the slow step, then the rest of the reaction happens pretty quickly. Okay, so my slow step is controls the rate of the reaction. RDS is rate determining step, and the rate determining step is the slow step because it takes time to happen. But once that happens, once I get over the hump for the slow reaction, then the rest of the reaction will happen pretty quickly. So far, so good? Okay. Now, let's keep going with this. Now, what I'm going to do, we're going to figure out the rate law, right? I'm going to put R theoretical. Let me write it nice there. Theoretical. And this R that we're going to do, this R theoretical that we're going to do, is going to be based on, this is key, is going to be based on RDS. And I will explain that in a second. Basically, if I want to figure out R theoretical, it will depend only on RDS because this is your rate determining step. This is the step that is going to hold you back. Once this step happens, the rest of the reaction will happen very, very quickly. Okay? So my R theoretical is going to be based on RDS because this is what's holding me back. Now, my slow step is step 1. Step 1 is my slow step. So my rate law is going to be the concentration of A times concentration of B. So I don't want to lose you. Pay attention. Keep paying attention. This is my slow step. I said step 1 is my slow step. So this is my slow step. I'm going to write the R theoretical, the rate law, based on the rate determining step, which is the slow step. Again, it's the same as before. Oh, I forgot to put K. Shoot. It would be R is equal to K times concentration of A times concentration of B. Okay. Now, if you remember before, when we were writing the rate law for the net reaction, we had to do experiment, and based on experiment, we would figure out the rate law and the orders. Now, for our theoretical, we don't have to do that. We're going to look at the steps. We're going to pick the slow step, the slow elementary step, and we're going to write the rate law just based on the slow step. Just based on the slow step, because this is what's holding you back. After this step happens, everything else is going to happen pretty quickly. Okay? Now, how did I know this is order 1? This is order 1 because we said that. We said for elementary step, you can use the coefficient to determine the rate law. For elementary step, this is one elementary step, you can use the coefficient to find the rate law. Okay? And this is my theoretical rate law. Okay, so far so good. Hopefully you got this down. Now, I said this is our theoretical. This is what we think is going to be the rate law of this reaction. How can I be sure that this is the mechanism and this is the rate law of this reaction? Here's how. You can run experiment and determine the rate law based on the net reaction. And if that rate law matches what you figure out based on the slow step, that means, yeah, this is a good mechanism for this reaction. That means this is a good mechanism for this reaction. I want to go over this one more time. I know you probably want to fast forward me right now, but don't. Resist it. Do not fast forward me. So, we decided, or we came up, that this is the mechanism. These are the elementary steps that leads to this net reaction. Okay? And we knew that this elementary step is a slow one and the second one is a fast one. So we wrote, and our theoretical is theoretical because we're not sure, because we haven't done an experiment yet. We write a rate law based on the RDS, because RDS is what's holding us back. Once this happens, everything else goes pretty quickly. So based on that, R is equal to K all the time. Concentration of A times concentration of B. Again, why did we ignore step 2? Because you have to do it based on the rate determining step, which is the slow step, which is step 1 in this reaction. So now I came up with my R theoretical. Now what do I have to do? Now what you can do, you can run experiment, find the rate law for the net reaction, and see if it matches what you decided. Okay? To see if it would match what you decided. Okay? So we're going to do experiment and then figure out the rate law for net reaction, and then see if matches, and then see if it would match the R theoretical. Okay, so you can do experiment, figure out the rate law for the net reaction, and then compare and see if it would match the R theoretical. Now, what happens if it does match? If it does match, what does that mean? What do you think? If it matches, what does that mean? If it does match, if it matches, then what that means is, that means this is a good possible mechanism. That means this is a good possible mechanism. This is a good possible mechanism. Okay, so I'm going to do experiment, figure out the rate law based on this, and then match what we thought is true. And then if they do match, then that means this is a good possible mechanism. This is so much easier than actually going to lab, doing all the experiment, and then figuring out the rate law for the reaction. But we should do that to see if it does match up. If it does match up, that means this was a good possible mechanism. So far so good. Okay, let's do another practice problem to make sure that you are on the same page as me. I know I'm going really slow. Hopefully you're not getting tired of that, but don't fast forward me. Listen to me. Here's my net reaction. NO2 plus CO going to NO plus CO2. That's my net reaction. Now, here is the proposed mechanism. Okay, so this was my net reaction. Here's my proposed mechanism. And I need you to remember, again, mechanism is how does this happen? It's not going to happen in one step. That's not going to be likely that everything just going to come together at one step. No, probably that's not going to happen. It probably happens in several steps. So the proposed mechanism is telling us how did we get here. This is a final product, but how did we get here? It's like cooking. When you see a dish, it didn't just happen, right? There was so many steps went into it. Sometimes too many steps. Here's the proposed mechanism I looked up for this. NO2 plus NO2 goes to NO3 plus NO. And then NO3 plus CO goes to NO2 plus CO2. And then the other piece of information that I found out was that the top one is my slow reaction and the bottom one is my what just happened? The bottom one is my fast reaction. Okay? What is the first thing we're going to do? The first thing we're going to do, we are going to add them together. I know I told you if you add up this together, you're going to get this reaction, but you always have to convince yourself. Don't ever take my word for anything. Well, except for lectures. But that was part of lectures. So, convince yourself. I want to add these two together. What can I cancel out? I can cancel out what? NO3, because they look exactly the same on both sides. Is there anything else I can cancel out? I can also cancel out NO. They're on the opposite side. I can also cancel out NO. Anything else? No. So to add them up, we cancel the one that we can. The ones that they appear on the opposite side, you can cancel this out. You can cancel this out too. So if I add it together, I get NO2 plus CO going to NO plus CO2. That is going to be my net reaction. Does this match up by that reaction on top? It does. It does match up the reaction on top. So we're good. So you convince yourself after you add these two together, you get the net reaction. So far so good? Okay. Now here's another question for you. Do we have any intermediate in this problem? And if we do, what is it? Think about this, think about this, think about this before you shout the answer. Okay. Now, what do you think? My intermediate is, hopefully you're saying NO3. I completely agree. NO3 is my intermediate. It does not show up my last reaction. Now, some people, they get tempted to say, oh, NO2 is also my intermediate because it gets cancelled out. But NO2 is not the intermediate because remember what was the definition of intermediate? It does not show up on the final equation. I do have NO2 in the final equation right here. So NO2, even though it does cancel out, I have another one of it. So it does end up showing up in my final reaction. I just have too many of it, so it had to cancel out. So NO3 is my only intermediate because by definition, intermediate is something that does not show up in the final equation. And even though you did cancel out one NO2, it does show up in my final equation, and that's not my intermediate. Okay. Now what we want to do, we want to write the rate law. I'm just going to write this down. We want to write the rate law expected. We want to write the rate law expected based on this mechanism. Okay, so we have a proposed mechanism and we want to write the rate law based on this proposed mechanism. How are we going to do this? Okay, now remember, to write the rate law based on the proposed mechanism, you have to look at what? You have to write the rate law based on RDS, right? It's going to be based on RDS. So again, it's going to be theoretical because we're not doing any experiment, right? So here is our rate law. And we said before that the rate law is going to be based on RDS. Now, which one is my RDS? The slow step is my RDS. So step 1 is what's going to be the slow step. So that's going to be my RDS. So far so good. So I'm going to write the rate law expected based on the mechanism. That's my R theoretical because I'm not doing experiment. It's going to be based on RDS. This is my RDS. You agree? This is my RDS. So I'm going to write the rate law based on that. R is equal K equilibrium. So K constant times NO2 to the power of 1 times NO2 to the power of 1. And like before we said, because we're using an elementary step, we're using one single elementary step to write the rate law, so we can use the coefficient as the order. Because we're using one single elementary step, so we can use the coefficient to write the rate law. Are we good so far? Okay. Now what I'm going to do, I'm going to clean this up. So my R theoretical, I'm just cleaning this up, is going to equal K times NO2 to the power of 2. I just add this up together to clean it up, okay? I'm actually going to write that word down. So all I did, I just clean it up. So later on, if you go back to it, because NO2 times NO2 says NO2 to the power of 2. I just clean this up. So this is what I end up getting for R theoretical. Okay? This is what I end up getting for R theoretical. Now, then what I have to do, what I can do experiment. I can do experiment for this reaction and then see if the rate law equation that I get based on the experiment would match this up. If it does match up, then that means it's going to be a good mechanism, right? So what I can do, and I'm going to write it down because I can do the R experiment, okay? Do experiment, figure out, and then see if it would match the R theoretical. And then if yes, that means we have a good mechanism proposed. Good proposed mechanism. So far so good. So figure out the R experiment, match it to R theoretical. If yes, they do match, then what you're going to do, that means it's a good proposed mechanism. Okay. Now, let's go back to this. Look at, and I know you're probably tired, but just give me like 1 more minute and then we're going to be good. Look at the net reaction for me. This is a net reaction, right? If you look at the net reaction, you have NO2 and you have carbon monoxide, right? If we look at the net reaction based on this, what is the order of NO2? The order of NO2 is second order. And what is the order for CO? Order for CO is 0 order. Okay, I know you are probably lost right now. So that's why I want to make sure you're not lost. So my net reaction, okay, this was my net reaction. I'm going to go back here. My net reaction. So when I said 2 minutes, I meant like 3 minutes. My net reaction is NO2 plus CO going to NO plus CO2. Okay? And my R theoretical, based on the rate determined instead, says my rate law is K times NO2 to the power of 2. Okay? Now, we want to compare these together. Again, I can do experiment and figure out our experiment, see if it matches to this. If it matches, yes, it's a good mechanism, and then we're good. If you look at this, I want to just look at this. This is my net. NO2 is in my net reaction. Now, based on this, NO2 is a second order. Based on this, NO2 is second order. Do you guys see that? Okay, so based on this, NO2 is going to be second order, because this one says it has a power of 2, so this is second order. Now, based on this, what do you think the order for carbon monoxide is? It's 0 order, because it does not show up on my final rate law equation. So this is one of the reactions. It doesn't show up in this equation. That means this is 0 order. Okay. Now, why is carbon monoxide 0 order? Does it make sense that it's a 0 order? It makes sense that it's 0 order because if you look at the carbon monoxide is part of the fast step. It is part of the fast step. The fast step does not affect the rate. The slow step is the big hump that you can get over. Once you get bigger the hump, it's just all downhill. It just go whoosh, it goes. So NO2, based on this, is a second order. And carbon monoxide, which is one of the reactants, doesn't even show up in this rate line. If it doesn't show up, that means the order was 0. Does it make sense that the order is 0? It does make sense, because we said when the order is 0, that means order of 0 does not affect the rate. And this is a good example, and it shows you why 0 order doesn't affect the rate, because carbon monoxide is part of the fast step. The slow step is what determines the rate, because you have to get over the hump, right? You have to get over the hump. Once you get over the hump, you just whoosh down. So this does not affect the rate, okay? It's a fast step, does not affect the rate. Okay? So, and this is our rate law. And I actually looked it up based on our experiment, and this does match up to our experiment. So this is a good proposed mechanism that's saying carbon monoxide is in a fast step, so it doesn't really affect the rate, but NO2 affects the rate. And as you can see, you have 2 NO2 coming together, so it's going to be a second order for NO2. NO2 really affects the rate, because the slow step is just NO2 coming together. The slow step is just the NO2 coming together. So yeah, it's a second order reaction. It has a bigger effect on the rate. Yeah, it has a bigger effect on the rate. Sounds good? Okay, I'm going to stop here. Really nice job. I think we got this down. We're going to continue with mechanism. We're almost there next time. But I think we need a break from chemistry right now. I will talk to you guys next time.